So let's go over the types of problems you'll be expected to know on your quiz. So in problem 1, given sine of theta is 1/8, with theta in quadrant 1, we want to find the other 5 trig function values using identities only. So let's start with the easier trig function to find, cosecant of theta. Since it is the reciprocal of sine, it'll be 8. Next, we want to go ahead and use the Pythagorean identity sine squared of theta plus cosine squared of theta equals 1 in order to find cosine and secant. So replacing sine of theta with our known ratio 1/8, we get 1/8 squared plus cosine squared of theta equals 1. 1/8 squared is 1/64. Subtracting 1/64, we get cosine squared of theta equals 63 over 64. Taking the square root, we end up with cosine of theta equals, now while the square root of 63 does not exist, it's not a whole number, we can simplify radical 63 since it is 9 times 6, so we get 3 radical 6 over the square root of 64 is 8. Then secant of theta equals 8 over 3 radical 6. And then all that's left to find is tangent and cotangent. Well, tangent of theta, another one of our identities, tells that it's sine divided by cosine. So that would be 1/8 divided by 3 radical 6 over 8. And we are dividing two fractions with the same denominator, so we are only dividing their numerator. So tangent is 1 over 3 radical 6. And cotangent of theta is its reciprocal, 3 radical 6. And we now have the remaining 5 trig ratios. And we only used identities. Next, we want to simplify some trig expressions. So when you're looking to simplify a trig expression, you don't necessarily have to write everything in terms of sine and cosine first. If there is a Pythagorean identity, typically we like to use that first before we rewrite in terms of sine and cosine. But our first example does not have any identities in it, Pythagorean identity, so we can go straight to writing in terms of sine and cosine. So we get 1 over cosine x minus sine of x times sine of x over cosine of x. Multiplying the sine of x times sine of x over cosine of x, we get 1 over cosine x minus sine squared over cosine. Our two fractions have the same denominator, which means we can rewrite it as a single fraction. So we get 1 minus sine squared of x all over cosine of x. Now 1 minus sine squared of x we can replace using Pythagorean identity. It gives us cosine squared of x over cosine of x. Cosine squared divided by cosine, one cosine will cancel and we'll be left with cosine of x, which is our simplified expression. Okay. So next we're going to simplify cosine of y secant of y minus cosine of y over secant of y. So first step, rewrite in terms of sine and cosine. So we're going to leave cosine of y times 1 over cosine of y minus cosine of y divided by 1 over cosine of y. Well, cosine times 1 over cosine is just going to give us 1 minus cosine of y times cosine of y, because we're going to flip the fraction in the denominator and multiply it to our numerator. So we end up with 1 minus cosine squared of y, and this is another Pythagorean identity. 1 minus cosine squared of y is sine squared of y. And this is our simplified expression. So next we have 1 plus cosine of alpha times cosecant of alpha minus cotangent of alpha. So in this case, my best first step is actually going to be to distribute everything first before rewriting in terms of sine and cosine. So we have 1 times cosecant of alpha, which gives us cosecant of alpha. 1 times negative cotangent of alpha gives us negative cotangent of alpha. We then have cosine times cosecant, so we get cosine alpha times cosecant alpha, and then cosine times a negative cotangent, so cosine alpha cotangent alpha. Now I can go ahead and rewrite everything in terms of sine and cosine. So we get 1 over sine of alpha minus cosine of alpha over sine of alpha plus cosine of alpha times 1 over sine of alpha minus cosine of alpha times cosine of alpha over sine of alpha. Now if I notice, every term that involves a fraction has a denominator of sine. So I know that I can write my answer as one fraction with a denominator of sine of alpha. So I get 1 minus cosine of alpha plus cosine of alpha minus cosine squared of alpha. So the 1 came from the 1 over sine minus cosine over sine plus the cosine times the 1 over sine minus cosine times cosine gives us cosine squared. Well, now a negative cosine alpha and a positive cosine alpha will cancel. So we're left with 1 minus cosine squared of alpha all over sine of alpha. And again, we're going to use a Pythagorean identity. 1 minus cosine squared is sine squared of alpha, still over sine of alpha. So a sine squared divided by a sine, one of the sines will cancel, and we will be left with sine of alpha. Now, if you chose to rewrite in terms of sine and cosine first and then distribute, you still should have had very similar steps and you still should have gotten the same final answer of sine of alpha. Okay. So last example, sine of 90 degrees minus x. So because we are subtracting, we're going to use the subtraction or difference identity for sine. So that is sine of x, so sine of 90, cosine of y, which in this case is x, minus cosine of x, which in this case is 90, times sine of y, which in this case is x. So sine of 90, from the unit circle, sine is always the y coordinate, so we get 1 times cosine of x minus cosine of 90 is 0 times sine of x. 1 times cosine is just cosine of x, and then the 0 times sine of x is just 0, so our final simplified expression is cosine of x. So let's go ahead and verify trig identities. So looking at the first example, we want to determine which side to simplify. Well, anything that is one term, we want to leave alone. So we're going to leave the tangent of b alone, and we're going to simplify that left side. So I'm going to start by rewriting my numerator in terms of sine and cosine. So we get sine of beta over cosine of beta plus cosine of beta over sine of beta all over, and then cosecant squared of beta I can write as 1 over sine squared of beta. So my next step is going to get my numerator to be a single fraction. So in order to do that, I'm going to multiply my first fraction by sine of beta and the second fraction by cosine of beta. So we end up with sine squared of beta plus cosine squared of beta all over sine of beta times cosine of beta all over 1 over sine squared of beta. So I'm going to kind of combine steps here. I can rewrite, I know sine squared plus cosine squared is 1. So we're going to get 1 over sine of beta times cosine of beta. And then I'm going to go ahead and change this to multiplication and flip my denominator. So it's times sine squared of beta over 1. So now I have a sine squared and a sine. One of those will cancel. So we're left with sine of beta over cosine of beta, which is going to give us tangent of beta. And that's what we wanted it to equal, so we have tangent of beta equals tangent of beta. So next example, tangent of x times cotangent of x minus cosine squared of x. So I'm going to rewrite the tangent as sine of x over cosine of x times, and then cotangent of x is going to be cosine of x over sine of x, minus, and I'm actually going to leave the cosine squared of x alone for now. I could use a Pythagorean identity to rewrite it as 1 minus sine squared of x, but that may actually mean more work for me in the end. So right now, because cosine squared is already in terms of sine and cosine, I'm not going to touch it unless I have to. So going back to rewriting the tangent and cotangent, I now have sine over cosine times cosine over sine, which are going to all cancel to give us 1 minus cosine squared of x, which is a Pythagorean identity, and we get sine squared of x equals sine squared of x. Now, if I had replaced that cosine squared of x with a 1 minus sine squared of x, we would have eventually gotten to the same result. It just would have added a couple extra steps. And remember, we always want to try to verify identities in the least amount of steps possible, even though that other method is still a valid way. So now we're going to use our sum and difference identities to find exact values. So to find cosine of 165 degrees, I want to either find two angles that add to 165 or two angles that subtract to 165. And there are multiple options here. So if you do not pick the exact angles I did, that's fine. Your final answer should still be the same though. So I am going to use x equals 120 and y equals 45 because 120 plus 45 is 165. So the addition identity for cosine is cosine of x, so cosine of 120, cosine of y times the cosine of 45, minus cosine of x, so cosine of 120, it's minus sine of x, sine of 120 times sine of y, sine of 45. So now we're going to use the unit circle. Cosine of 120 degrees. So remember, from the point on the unit circle, cosine is always the x value. So we get negative 1/2 times radical 2 over 2 minus sine of 120 is always the y coordinate of your point. So radical 3 over 2 times sine of 45, which is radical 2 over 2. So negative 1/2 times a radical 2 over 2 is a negative radical 2 over 4 minus a radical 6 over 4. And writing our final answer as a single fraction, we get negative radical 2 over 6 all over 4. And that is the exact value of cosine of 165 degrees. Now, if you use different angles and you got negative radical 6 minus a radical 2 all over 4, that is still an equivalent answer and it is still correct. Okay, so now we want to find tangent of 23 pi over 12. So looking at your unit circle, you want to find two radians we can add to get to 23 pi over 12. So I'm going to let x equal 5 pi over 4 and y equal 2 pi over 3. Because if I rewrite 5 pi over 4 in terms of a denominator of 12, we get 15 pi over 12. And if we rewrite 2 pi over 3 as a denominator of 12, we get 8 pi over 12. And a 15 pi over 12 plus an 8 pi over 12 is 23 pi over 12. So using the addition identity for tangent, we are going to get tangent of x, so tangent of 5 pi over 4, plus tangent of y, tangent of 2 pi over 3, all over 1 minus tangent of x, so tangent of 5 pi over 4, times tangent of y, which is tangent of 2 pi over 3. So now I just have to plug in the ratio for tangent. So tangent of 5 pi over 4 is 1, plus tangent of 2 pi over 3, which is going to be a negative radical 3, all over 1 minus 1 times a negative radical 3. So I can rewrite the numerator as 1 minus radical 3, all over my denominator is going to change to 1 plus radical 3. You could leave this as your final answer, but if you choose to rationalize the denominator, I would multiply the top and the bottom by the complex conjugate of our denominator, so 1 minus radical 3. So we're going to get 1 times 1 is 1, minus a radical 3, minus a radical 3, then plus 3, all over 1 times 1 is 1, minus a radical 3, plus a radical 3, and then minus 3. So combining like terms in the numerator, 1 plus 3 is 4, and we get minus 2 radical 3, all over 1 minus 3 is negative 2, and then the negative radical 3 and the positive radical 3 cancel. And I can go ahead and divide 4 and 2 by the negative 2, so we end up with negative 2 plus radical 3. So this is the exact answer for tangent of 23 pi over 12. You can also use the answer of 1 minus radical 3 all over 1 plus radical